in space. Okay. Vectors, well, we'll look at that. Vectors are going to be denoted by ordered triples instead of ordered pairs. And remember, the alligators, I can't remember what they're officially called. The alligators notate that they are a vector instead of a coordinate, right? Okay. Now, we're not going to have to plot vectors, but it will be good practice for our point. So let's just look at. Okay. Since this is, what form is this? Do you remember? What? There's two different forms for our vectors.
Standard. No.
That's a great guess.
Rectangular. Component form.
Good. Component form. So the vector -1, 2, 4 would look like this. Right? Okay. What if we knew that we had the point P of 2, 3, 4 and the point Q of -1, 0, 5, what would the vector PQ be? How do we find vector PQ? No. Good. No.
I remember doing
Subtract. What do we subtract? What order?
Terminal minus initial.
Terminal minus initial. So that since this is the vector PQ, which one would be our terminal? Q would be our terminal, P would be our initial. So to get the vector PQ, we would take -1 minus 2, 0 minus 3, and 5 minus 4 to get our vector -3, -3, 1. So, for fun, we wanted to plot that vector. -3, -3, 1. Which really is behind the z-axis, right? In octant number
3.
Awesome. Good job. Okay. Remember, we had the i's and the j's as our vectors. Okay. We are still going to have I and j, but now we have vector k. All right. So vector I is 1, 0, 0. Vector j is 0, 1, 0. And vector k, 0, 0, 1. Okay. These are unit vectors in just one direction. Okay. This is along the x-axis. This one sits along the y-axis. K sits along the z-axis. Okay. So, the second form we write vectors in is the linear combination of these unit vectors. Okay. So instead of writing -3 common, the vector 3, comma, negative 5, comma, 2, we could write it as 3i minus 5j plus 2k. And just for practice, 3, negative 5 would be here, and then up 2. So our vector lies in octant
4.
4. Okay. All right, so now the fun stuff. Let's remember a couple things from chapter 6. Okay, magnitude of a vector. What does magnitude mean?
The size, the distance.
The length of our vector. Okay, so let's remember what we did back when we were in 2 dimensions. If we had a vector, v1, v2, okay, how did we, first of all, what was the notation for magnitude?
It's like double absolute.
Good, double absolute values. So the magnitude of v, how did we find it? Yes. Square root of your vertical component squared plus, or your horizontal component squared plus your vertical component squared. Okay? So if we are in 3 dimensions, what's it going to be?
v1 squared plus v2 squared.
Okay. Okay, so let's find the magnitude of -1, 2, 2. So the magnitude of v would be the square root of -1 squared plus 2 squared plus 2 squared, which would be what? So the length of vector v is 3. All right, let's remember how to do some operations with our vectors. Okay, we can add, subtract, and multiply by a scalar. That's what we're going to talk about first. Okay, so in example number 1, we are going to subtract u and v. U is the vector 2, 1, -2, 3. V is the vector 0, 5, -2. Okay. So if we subtract the 2 vectors, what's our process? What do we do? So we subtract like components. Okay, we'll call those components. The x's, subtract them, the y's, subtract them. So if we're taking u minus v, then what would our x component be? Our y component? And because we're subtracting -2 minus 5.
Oh, yeah.
Okay. And then our y, or our z's. 5 because that's 3 minus negative 2. Okay? Here, in the second example, I have 5v plus 2u. So 5v, what do we do? Okay, multiply v by 5. So 5v would be 5, negative 10, 15. What?
The first one is 0. It's 5.
Oh, 5v. What was I doing? I was doing 5u. Thank you. 0, 25, negative 10 would be 5v, right? Thank you for fixing that for me. 2u would be what? 2, negative 4, 6. So then we add them together to get 2, 21, negative 4. All right. Next, a unit vector. What's a unit vector? Okay, those i's and j's are unit vectors because they have what?
A magnitude of 1.
Okay, they are unit vectors because they have magnitude of 1. Okay, so if you recall back to chapter 6, we took vectors and we found unit vectors in the same direction. Okay, do you remember how we did that? We can take 1 over the magnitude of our vector and multiply it to our vector, and then we will have a unit vector in the same direction as v. Okay. If you remember back to vectors, as long as our vectors are scalar multiples of each other, then they are parallel. Okay, they're going in the same direction, or they're either same direction or opposite. If it's negative, but as long as they're a positive scalar multiple of each other, then they're going in the same direction. So this 1 over the magnitude is the scalar multiple we're going to use to make it be a unit vector. So let's go back to our example from before. Vector v was negative 1, 2, 2, correct? And what was the magnitude of v? 3. So for our unit vector, we would take 1 over 3 and multiply it to our vector to get negative 1/3, 2/3, 2/3. Okay, so this is a unit vector because the magnitude is 1, if you want to calculate it. All right, and it's in the same direction as v because it's just a scalar multiple. All right. 3 more slides. Can you handle it? This one's easy. Dot product. Okay, so let's remember what it was like in 2D. If we had our vector v, and we were taking the dot product with our vector u, then what would we do? We add it, but not yet. We have to do what? Okay, so we're going to multiply the components and add them together. So v1 times u1 plus v2 times u2. Okay, so multiply the x's, multiply the y's, and add those two products together. Okay, so in 3 dimensions. Yes. Except you're going to have 3 products you're going to have to add together. So here's the example we're going to do. So remember the dot product, you'll see the dot in between, right? Okay, so talk me through how to do this. First, we're going to take -1 times 3, and we're going to add it to 2 times 2, and we're going to add that to 2 times -1. So our dot product is -3 plus 4 minus 2, which is okay. So far this has been kind of just a big review, just with 3 dimensions, right? Okay. Do you remember what we could do with a dot product? Fun things, you're right. We had a formula where the dot product was in it. Do you remember? Finding the angle in between vectors. Does anyone remember it?
It's something over something, the magnitude of it. Oh, I got it. Dot product
Uh-huh.
over
Uh-huh.
Magnitude of u, magnitude of v. Equals the cosine of theta.
Yes. The cosine of the angle in between equals the dot product over the magnitude of u times the magnitude of v. So I would like us to find the angle in between these two. Okay. So I am going to have, let's see, pods 1 and 2. You guys are going to find me the magnitude of u. Pod 3, you're going to find me the magnitude of v. 4 and 5, please find me the dot product of u and v. Magnitude of u. Magnitude of u.
three.
What?
I didn't know I had to finish that.
Okay. Okay, so we have a dot product of 3. We all agree on that. Did you get that? Okay. Magnitude of v is radical 10. Magnitude of u is radical 5. Okay, do we all trust each other to work together?
I don't trust Joey.
I don't trust Joey.
Well, Emmy double checked Jenna, so we're good.
No, she didn't. She was doing that. That's why she double checked.
So the cosine of theta is the dot product over magnitude times magnitude. So how do we actually find the angle?
Take the second.
Inverse cosine of this. I would write inverse cosine of 3 over radical 50. Just make this radical 50 in your calculator. So make sure you are in degree mode, and please take the inverse cosine of 3 over radical 50.
She asked too many answers, Joey, we can do that. You say degree mode or radio?
Degree. What did you say, Amy? Okay, you can't write 3 divided by square root of 5 times square root of 10 unless these are in parentheses. So what I would do, Joey, I would just say 3 over radical 50.
The important thing is that you try, the more important thing is that you fail.
What happens if our dot product is 0?
I'm gonna talk to each other. Aren't they like the same? Oh, number one.
What's the inverse cosine of 0? Where is the cosine 0? 90 degrees. So if the dot product is 0, this becomes 0, and our vectors are perpendicular, or as we like to call it, orthogonal. Okay? What if theta is 0 degrees or 180 degrees? What does that mean? Well, they're not the same line, but they're going in the same direction, or they are parallel. 0 degrees means they would go the same direction. 180 means they're in opposite directions, but either way, they would be parallel vectors. Okay? Also, like we talked about before, if they are scalar multiples of each other, then they are parallel. Okay? A positive scalar multiple would be same direction, negative would be opposite. Okay? So using that, this is something that we did not do. Okay? I would like to know, okay, if I give you 3 points, how could we figure out if they are collinear? Given everything we just talked about, I give you 3 points. How could I figure out if they are on the same line? Okay, and how would that help us? Okay, well, if I have 2 vectors that share a point, and they are going in the same direction, what has to be true? They have to be on a line, right? So if I can make 2 vectors out of these 3 points and show that they are parallel, since they share a point, they must be lined together collinear. Okay? So, we actually don't even have to find an angle as long as we can tell that they're parallel because they're scalar multiples of each other. That'll save us some work. So what 2 vectors would you like to look at? Okay, PQ would be 1 vector. These are points that we're trying to figure out if they're collinear. So we can make a vector out of PQ. What would that vector be? -2, 1, -3. Terminal minus initial. So this is vector PQ. Okay. Now let's look at a second vector. We can either make PR or QR. What do you want?
QR.
QR sounds lovely. And that vector would be what?
4.
Oh, I know, just 4.
4.
2, 6.
Okay. So, if I look at 4, -2, 6, do you agree that that is the same as -2 times -2, 1, -3?
Yes.
Yes. Why did I pick -2, 1, -3? Because that's PQ up here. So, since QR is a scalar multiple of PQ, then PQ is parallel to QR, and PQ and R are collinear. We have two vectors that share a point and they're parallel, so they have to be all together in a line. Alright? Okay. So this is really like the one newer thing that we talked about today. Okay. Everything else has been just kind of touch-up review. Right? Just with a vector in 3 dimensions instead of 2. Okay? Alright, so it is 8:36. We have until 53. Here is your homework.